Recording has started. All right, and then Bryant, if you could mute your mic while I record and only unmute it and ask when you need to. That way, if you make rustling or any little noises on there, it won't interfere. Oh, I see you did already. Good job. I hope. Are you still on, Bryant? Or, oh, Bryant, it shows that you're offline. Rats. Bryant lost connection. All right, well, we'll get started, and I'll see if I can get him back in again. Okay, so good morning. We're recording. It is Tuesday the 22nd, yeah? And we're on page 454 in print and page 454A in Braille, and it's in volume 41. If I say this, those Stormy and Angelica and all those others, Tanners, probably listening. Okay, so this whole section is about parts of circles, and some of the parts of the circles they'll sound familiar. You have worked with radii, radius, diameter, circumference, centers. They're going to introduce a new term in this section called a chord, and then we're also going to discuss the basics of the diameter and the radius, which should sound familiar to you, and how you obtain a radius or a diameter, and then also labeling circles very carefully in print and in Braille, and then we're going to talk about concentric circles, and that's kind of it's like a section on anatomy really of a circle. So the first page here, 454A, it just has a circle. And it says all points on a circle are the same distance from a center point. So here's your circle, and you have your center point, and they've labeled this center point O. And then they've drawn two radii, one at about the 11 o'clock position, and it goes to point A, and one at about the 1 o'clock position to point B. This is two radii of infinitely many radii. But what it's showing is that from the point in the center, there's the O point in the center to point A, and from the O point in the center to point B, those are the same distance. And no matter where we take a line from the center O and draw it to the outside of the circle, it will always be the same distance. So if you create that same distance all the way around, you create a circle. Right? So that gets us to the definition. Oh, and then the measures, they say below, the measures of segment OA and OB are the same. That is, OA equals OB. So turn the page, and then we get the official geometric definition of a circle. So we have a circle in the center of our page just to represent with center point P. And the official definition of a circle in words up at the top is a circle is the set of points in a plane that are a given distance from a given point in the plane called the center of the circle. So the fancy language for a circle is we've got a point in a plane, and there's a set of points that are the same distance from that point all the way around connected together. And that's a circle. And in symbols, so down below, just below the circle, especially in Braille, this is very interesting. You're probably used to seeing shape indicator C for a circle, but in geometry we get even a little fancier. And we put a little point in the circle, and then we put a P next to it. So in Braille, what we have to write is EDC, and then a punctuation indicator, 4, 5, 6, and then an ED, and then a dot 1, 6, and then an ER, and then a capital P. And that's a lot of information for saying circle P. All right, circle P. And it's fancy. In print, it's a little tiny circle with a dot in the middle of it to represent the center, and then a big capital P next to it. And so that's what they're trying to show in Braille. All right? Okay. And it says, note that a circle is named by its center. The circle above is named circle P. So turn the Braille page to 454C, and hold on one moment. Let me get Bryant back on the line. He just said, I think I lost it. There it is. And so we're on 454, and now it's discussing there are three kinds of segments. So this is where a couple of them are going to sound familiar, and one of them is probably new to you. A radius is the segment whose endpoints are the center of the circle. So we've already seen that with the first drawing today with OA and OB. Those were radii. A chord is a segment whose endpoints are on the circle. That's going to look a little different to you. And a diameter is a chord that contains the center. Hi, Bryant.
Hi.
We're back. If you could use your mic on your end and only turn it on when, or I can mute it on my end. There we go. I muted your mic, and I'm only going to turn it on if I need to ask you a question because I'm recording, and then that way if you turn pages or whatever, your microphone doesn't take over in the recording. Come on in, Damien. So we are on page 454C. I'll bring you up to speed, Brian. It's just a Braille page. And we looked at a circle with center P and its definition. And now we're going to look at three pieces of a circle, the radius, the chord, and the diameter. All right? So let's go look at each one. In Braille, turn the page 454D. In print, it's at the bottom of the page. There's three of them, one right after the other. The first one is a drawing of a radius, and I'm sure you've seen this before. I saw it a few moments ago, but I'm sure you've seen it in pre-algebra class and algebra class. We have a circle K, and there's a radius coming from center K to point A at about the 8 o'clock position. And that's showing a radius. And a radius can be anywhere in your circle coming from the center to any point on the outside of the circle, right? And it's always the same distance, always the same. And down below in symbols it says KA, segment KA, is a radius of circle K. And there's that funny little circle way they do it in print. It's EDC 456 ED16ER and then capital K, all right? So that's a radius. You've seen those before, yes? And then go to the next Braille page, 454E. This is a new one probably for you. This is a chord. And a chord, there's a chord up going from about, just about 9 o'clock to 1 o'clock. It's going from point J to point R. Notice that it does not go through the center K. So a chord will have two endpoints anywhere on the circle. We could have a bunch of different weird looking chords all over this thing. And they can be all sorts of different measures. Right? So they say down below in symbols that JR is a chord of circle K. Now turn the page, and this one should look familiar. This is a diameter. A diameter is also a chord. So remember you learned that an equilateral triangle is also isosceles. A square is also a rectangle because it meets the definition. A diameter meets the definition of a chord as it goes from one endpoint to endpoint on the circle anywhere. But it's a special chord in that it goes through the center. So notice there's a diameter going from about 10 o'clock, which is at point T, to about 4 o'clock, point G, and it's going right through the center K. That's a diameter. From K to T is a radius. From K to G is a radius. All together, from T to G or GT, is this special chord called a diameter. Abby?
When you say the diameter is chord,
it's a chord because it meets the definition of a chord.
Like the chord is supposed to point.
A chord can include the center point, and then it's called a diameter. Just as an equilateral triangle is an isosceles triangle, but we more specifically call it an equilateral triangle. Just as a square is a rectangle because it meets the definition of a rectangle, but we call it a square. A diameter is a chord, but we don't call it a chord, we call it the diameter. And then a chord, if it's just a chord, it's anywhere else, not going through the center. All right? Okay. So notice you've learned this before in pre-algebra, but diameter is two radii together, isn't it? K to T and K to G. So if you double your radius, you get the measurement of your diameter. Or if you take your diameter and divide it in half, you get the measure of the radius. So that's what we're going to do some identification, and then the next little section of this lesson is going to talk about how to, find the radius and the diameter. So turn the Braille page to 455, turn the print page to 455, and now you're going to identify all sorts of things going on with this circle. So we have this circle Q. Find your circle and find your center Q. And notice from Q to about 1 o'clock, it goes to Q to B. What is that? What is QB? A radius. Good. And then notice it goes from Q to A at about the 10 o'clock. What is that from Q to A? A radius. Then if you go from Q to C, which is down at about 4 o'clock, what is that? Another radius. And then from A through Q to C, what is that? It's a chord, but it's also AQC. All the way from A to C, 10 o'clock to 4 o'clock is a chord, but because it goes through the center, what is it called? Diameter. Good. Then go back to A. Jess, are you finding these? And then go immediately straight down to D. What is that? A to D. We're on page 455. A to D. Go from 10 o'clock and then straight down to about 7 o'clock. It's a chord. All right? So you identified all the parts of this circle, and that's what that example just did. So,
that's why.
Got it? Yeah. All right, so turn the page, and we got to do a little reading. After the your turn, it says suppose. So 1, 2, 3, fourth line down in Braille, the middle of the print page. It says, suppose the radius PQ of circle P is 5 centimeters long. So the radius of PT is 5 centimeters, also 5 centimeters. Then the diameter of QT is 5 plus 5, or 10 centimeters long. Notice that the diameter is twice as long as the radius. This leads to the next two theorems. And you've done this again and again and again in pre-algebra class and algebra class, where you've discussed that diameter is twice the radius. But it just shows you that in a drawing. It has circle P down here at the bottom, and from P to Q up to 1 o'clock position, they're saying that is 5 centimeters. And they're saying, well, then that has to equal P to T, which is also 5 centimeters, because all radii are equal. They're all equal distance around the circle. So if you add the 5 and the 5, then the diameter QT got to be 10. All right? And they have some couple extra radii on this, P to S and P to R, but we don't really care about those. They're just having you notice you can have a whole bunch of radii. All right. So it has two theorems on the next Braille page, 455B. We're going to have theorem 11-1 and theorem 11-2. And a theorem 11-1 just says all radii of a circle are congruent. Got to state it. We're geometrists now, right? So we can be attorneys, geometry attorneys. So therefore, PR is congruent to PQ, is congruent to PS, is congruent to PT in that last circle. All radii are always congruent. They're always the same of any circle. And then 11-2, the measure of the diameter, D, little d, of a circle is twice the measure of the radius, R, of the circle. And then it gives you a couple formulas. D equals 2R, or we can solve for R, therefore we divide by 2. 1/2 of D equals R, for D divided by 2 is R, all right? So we practice that in the next example, number 3, down at the bottom of this Braille page. It says, in circle T, CD is a diameter. If CD is 42, find TC. So you have a page, you turn the page, Braille page 455C. They have a circle. It said in circle T. CD is a diameter, so from C to D, which is from about 7 o'clock to 1 o'clock, they said that is 42. So what is TC? Well, we know that the radius is half the diameter, so what's half of 42? 21. And they go through the proof of it. They say, well, D equals 2R, because the definition of a radius. So they start using the substitution property. They say CD, they substitute that in for D, equals 2 times TC. Then they substitute in the values. CD is 42, 2 times TC, divide by 2, use your division property of equality on both sides, and 42 divided by 2 is 21. That's the fancy proof of it. In your head, you could quickly go, oh, well, that's half of 42, which is 21. So in the your turn, it asks in circle T, so the same circle, TM is a radius. So TM goes from the center till about 11 o'clock. TM is a radius, and that's 15.5. So if that was 15.5, if you were given that a radius was 15.5, it says find CD. So CD is a diameter, and you know a radius is 15.5. What's your diameter? What do you need to do? You double it. So 15.5 times 2 is 31. All right? That was on the next Braille page, and then there's a page break for 456. All right? 456. Now we put an algebra link in on it, which is really good. This is more indicative of what would be on an end-of-course exam. Having your diameter to find a radius, or doubling your radius to find a diameter, might be a question. I doubt it, because it's so basic. But what they'll probably do is use variables. All right? So it's asking us in this example to find the measure of the radius PC if PC is 2x and AB is 6x minus 28. So we have one more page over to look at the drawing on 456A. 2 pages over, Abby, 456A. So let's look at our drawing and really put our geometry and our algebra brains on how to solve this. We have circle P. There's a lot going on in this circle, but just be very careful. From P up to B at about the 1 o'clock position, and then back down to A at the 7 o'clock position. They're saying off to the side with a little light bracket, and then the Braille kind of ran into the circle, that this is 6x minus 28. So your diameter is 6x minus 28. And then from P to C at about just above the 3 o'clock position is 2x. So you know that the diameter is 2 times the radius. Always, 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 right? So you substitute in that information. The diameter is 6x minus 28. And you know that has to equal 2 times the radius, which would be 2x. So 2 times 2x. So they walk you through that proof on the next page. So let's go through that very carefully. So we're on 456B. So the very first thing it says is diameter equals 2R. Now we're going to use the substitution property and say, well, AB is the diameter, and that equals 2, open paren, PC, the radius. We're replacing in those segments. Then we're going to do the substitution property again with the values, the expression. We substitute in 6x minus 28 because that's AB equals 2 times 2x because 2x is PC. That's replacing using our substitution value, right? Then we're going to simplify. We're going to do some algebra. 6x minus 28 equals 4x. Because we went 2 times 2x, right? Then you notice you've got x's on both sides of your equation. So they subtract 6x on the left, subtract 6x on the right to move it over. So we are using the subtraction property of equality. 6x minus 28 minus 6x equals 4x minus 6x. Basic algebra. We end up with negative 28 because it was a minus 28 on the left. Negative 28 equals negative 2x. Because positive 4x minus 6x is negative 2x. So negative 28 equals negative 2x, simplified. We're going to divide by negative 2 on both sides using our division property of equality. And negative 28 divided by negative 2, a negative divided by a negative is a positive. The answer is 14. So x equals 14. Now, that's not the answer to the question. The question said find the measure of the radius. You have to substitute back in the 14, PC, down at the very bottom of the page in Braille, PC equals 2 times 14, because PC equaled 2x. So 2 times 14 is 28. If it asked you for the diameter, you double that, right? 28 is 56 for the diameter. So be careful that an end-of-course exam might ask, find the value of the radius, and you find 14 and move on because one of the choices was 14 and that wasn't the right answer. Yes, Damien? All right. The next bit of information is in regards to concentric circles. And because all circles have the same shape, any two circles are similar. However, two circles are congruent if and only if their radii are congruent. If their radii are not congruent, they're called concentric. One can fit inside the other. So this is an example, this drawing down below is an example of concentric circles. It's showing a big outside circle. They both share the center R. And an, just wrote a B. They both share the center R. And an inside circle. And notice from R to S, which is at about 1 o'clock, is the radius of the little inside circle. And from R to T, at about the 4 o'clock position, is on the outside circle. That's the radius of the outside circle. It's just demonstrating to you that circle R with radius RS and circle R with radius RT are concentric circles. They're similar, but they're not congruent because they don't have the same radius. So therefore, one is smaller than the other, and you can fit them inside of each other, and they're called concentric circles. All right? You've got to memorize that vocabulary. Okay? Do you think you're okay with radii, diameters, centers, all that good stuff? All right. So, finding x. Well, you gotta put your algebra brain on, and you gotta make things equal to each other, or make them equal to 2 times radius. Always start with the formula. Diameter equals 2r. Write it out. Then substitute in the values. What is the diameter on that last one? 6x minus 28. What is the radius? 2x. 2 times 2x. Put your algebra brain on and do the algebra. Do not flush the algebra. Algebra exists from here on out. Even when you learn to be a teacher, you will have to take several classes, math classes, and you will be using algebra. Don't flush the algebra. All right, let's get ourselves to page 462. I believe it's still in this. Yep, still in this section. We're going to do 2 sections today. 462. And I believe it's 462A. It is. We're going to talk about arcs and central angles. And this is absolutely crucial and new information for you about circles. It's very interesting. And it's stuff you just got to memorize. All right? We're going to practice it. We're going to learn about it today, practice it a little bit, and then we're going to practice it some more tomorrow and take a quiz. 462A. All right? 462A, same volume. And it says up at the top, a central angle. A central angle is formed when two sides, it's actually 3 lines now, not totally all the way at the top, right? A central angle is formed when 2 sides of an angle meet at the center of a circle. Each side intersects a point on the circle, dividing it into arcs that are curved line. All right? We're going to discuss a minor arc and a major arc, and I'm even going to show it to you in this drawing, and then we're going to see more drawings that talk about it. Let's really just work our way through this one drawing on this page, and I can get us through most of the information in the next few pages. So you have a circle O in this page. Find your circle and your center O. And from O till about the 2 o'clock position is the first radius they indicate, OP. Right? OP. And then from O to Q at about the 4 o'clock position, they have another radius. And the angle that is formed, POQ or QOP, they've labeled that in the center a central angle. Okay? Central angle. That's a central angle. All right? So POQ or QOP is called the central angle. All right? Between those two radius. You've been looking at angles since chapter 3, right? So POQ or QOP is a central angle. All right? Inside, between the P and the Q, is a measurement. That looks like it's probably close to 45 or 50 degrees. Okay? All right. That's called the central angle. On the outside of the circle, there are two things going on. There is a minor arc and a major arc. So from P at the 2 o'clock position to Q at the 4 o'clock position, if you just feel that on the outside of the circle, part of the outside of the circle, that's called the minor arc. The minor arc. And then if you go from P and you go counterclockwise around the circle and follow it all the way around, all the way around, all the way around back to Q at 4 o'clock, that's called the major arc. So Abby, put your hands on P and go counterclockwise to your left, all the way around the circle to Q. That's called the major arc. Okay? If you start at P again, and go clockwise, that's the minor arc. Yep, because it's smaller. Yep, okay. So minor arc, major arc. And those are very important to distinguish because that helps us figure out what their measurements are. Okay? So turn the page, and a paragraph of information talks about these two terms, these three types of arcs. There's one more arc that we're going to look at in regards to the circle. So there's three types of arc. The minor arc. Oh, you turn 2 page fast. Turn back. We're on 450 or 462B. Okay. There are three types of arc. Minor arc is part of the circle in the interior of the central angle. So Abby, you noticed it was the little one, right?
There's no circle like that.
No, there's not. We're just reading about it. Okay. The major arc, it's less than 180 degrees. The major arc is the part of the circle on the exterior of the central angle. So that was the big one that went counterclockwise. And semicircles are congruent arcs whose endpoints lie on the diameter. The major arc's going to be bigger, sometimes, not always, okay, but greater. And then, yeah, it is. A major arc is always going to be greater than 180. A minor arc is going to be less than 180. And a semicircle is going to be exactly 180. So let's look at all those in the next few pages. Now we can turn the page. 462C. This is showing the same circle. It added an extra point on here for us to just kind of distinguish some things. Notice that there's a heavy dotted line from P to Q, or no, G, sorry, P to G. They extended the radius into rays to kind of help you realize that these are, yes, indeed, angles, right? We have circle A. And then there's a point up at 11 o'clock at R that they just threw in there to kind of help us distinguish. Now, P is at about 2 o'clock, G is at about 4 o'clock. In symbols down below, they're telling you the measure of arc. Now this is new symbols. Arc PG. So notice measure .5, capital P, capital G, overhead indicator 126, ED.1 for arc, terminating symbol 1, 2, 4, 5, 6. That means arc PG, measure of arc PG, minor arc PG. They only use 2 letters for a minor arc. Is less than, the less than symbol, 180. So the measure of capital PG with a little arc over it in print is less than 180. In Braille, you have to use a .5 and a terminator to show your PG has an overhead indicator EDA over it. So that means so P to G is the minor arc. P to G, not that way. P to G, the heavy dotted line, is the minor arc, and it's always less than 180. Turn the page. Major arc, the other side. So they do the same exact circle, and then they heavily dot the major arc from P to G, which is counterclockwise. We have 2 rays, OP and OG, that are the radii of the circle, but then they extend them beyond the circle to show you have an angle. And there's a point R. They always throw in another point because we have to name a major arc with 3 points. So they'll throw in another point for us to name it. So this is circle A, and we have PRG or GRP, however you want to name it. Notice down at the bottom it says the measure, little m, .5. Capital P, capital R, capital G, overhead indicator 126, EDA, ER, terminating symbol, is greater than 180. So the measure of the major arc is always bigger than 180. Notice how it goes way more than past half the circle. And it's measure of P, R, G with an arc over the top of it. That's what the overhead indicator EDA stands for, because in print it's PRG with a little mini arc over it, is greater than 180. Okay? So, yes?
That is a center point for the but this will R.
No, but it could. But we don't want it to because we're using R to name our major arc. PRG. We got to name our major arc with 3 points. We couldn't say the measure of PG is greater than 180 because PG goes from clockwise from, it's a minor arc. Minor arcs are named with 2 points. Major arcs are named with 3 points. Okay?
So minor arc always less than 1.
Minor arc is always less than 180. Always
180.
greater than 180. And then the next page shows the semicircle. So we have our same circle A, and we have a diameter going from P to W from about 2 o'clock to 8 o'clock. They're showing a line. That's a diameter, right? And they're showing a heavy dotted line counterclockwise from P to W going through point R. And that's showing a semicircle. There's another semicircle from PQW on the other side. They're reminding you that semicircles are always equal to 180. That should make common sense. Half a circle is 180, isn't it? Why is it half a circle 180?
Because the whole circle is.
Excellent, Jess, because a whole circle is 360. So they have a radius A to G here that they've put in there. They're not talking about that. They're talking about PRW. We could talk about PGW. That's also 180. So whenever you get half the circle, the arc is 180. So the measure down below, the measure of PRW, arc PRW equals 180, because this is a semicircle. It's going from one point of the diameter to the other point of the diameter, right? Always 180. Using the same Braille, measure, .5, capital P, capital R, capital W, with an overhead indicator 126, EDA, ER, is equal to 180. All right? Now down at the bottom, a paragraph of information to kind of summarize this up. Note that circle A, 2 letters are used to name the minor arc. but 3 letters are used to name the major arc and semicircle. These letters for naming arcs help us trace the set of points in the arc. In this way, there is no confusion about which arc is being considered. Depending on the central angle, each type of arc is measured in the following way. Okay? So then we get definition of an arc measure on the next page, 463. 463. Definition of arc measure. So number 1, the degree measure of a minor arc is the degree measure of its central angle. If the central angle is 60, the minor arc is 60. The degree measure of the major arc is 360 minus the degree measure of its central angle. That should make sense. It's the other side, isn't it? So if the central angle is 60, the other side is 300. So the major arc is 300. And the degree measure, number 3, of a semicircle is 180. Always, always, always. So knowing these 3 things and using logic, using deductive reasoning, of course this makes sense. If a minor arc equals the central angle, the major arc is going to equal the central angle subtracted from 360. So the next example walks you through that. Right? So it says in circle circle R. So we have on the next page 463A. 463A. There's a lot going on 463A in the circle, but we can figure it all out. All right? Circle O. There's a point just before 12 o'clock at, circle R. There's a point at O. And then there's a point at N at about 1 o'clock. And then there's a point at T at about 4 o'clock. And then there's a point at K at about 7 o'clock. Off to the right, they have indicated the measures of some things. They have a little light line pointing into the central angle ORN. That's the very top central angle. And they're telling us that that's 42 degrees. So if you know that central angle is 42 degrees, then from O to N, the minor arc ON is also 42. They're indicating from N to T, clockwise, N to T to the right of the triangle, that minor arc NT is 89 degrees. If you know that minor arc is 89 degrees, you know the angle opposite inside of it, NRT, the central angle, NRT or TRN, is also 89 degrees. They didn't tell us anything about TRK or TK as we go clockwise around the circle. But when we get to the next position, K to O, so from 7 to about 11 o'clock, that central angle they've labeled 138 degrees. So you know KO is also 138. So knowing all of those, we could figure out TK. Because we know we have 138, 42, and 89, and we're missing one angle or one arc. Well, what's the total that has to be all the way around? 360, right? 360. So we're going to add 138, 42.
1, 3, 8 plus 4, 2 plus 8, 9 equal 269 minus 360 equal minus 91.
91 is left, isn't it? So we know from T to K is 91, and that angle, TRK, is 91, isn't it? We want to minus the 42, the 138, and the 89 all together, and we get 91 degrees left over. That's what you got to play with. You got to notice that you're given certain measurements, and you can subtract from 360 and find the missing measurement. All right? And that just plays into that we can use the angle addition postulate, which you learned way back in Chapter 3 and you reviewed in a recent email. That you have two angles together, you can add them together to equal a big angle, right? Okay? So we got all these angles together. We can add them together to equal the whole 360 all the way around. Okay? All right? So turn 2 more pages and get to the 463C. Let's see. No, I'm sorry. 463D. And it discusses the Arc Addition Postulate. 463D. It says the sum of the measures of 2 adjacent arcs is the measure of the arc formed by the adjacent arcs. That's fancy language for saying you have 2 arcs side by side. You add them together, you get a bigger arc, right? If you have 2 angles side by side, 2 adjacent angles, you add them together, you get the big angle. Angle addition postulate, arc addition postulate. They better coincide, right? So it shows you that in a drawing. It has a circle, and in symbols, it's showing that one of the angles, PCQ, is right next to QCR, and those combine to be, so RQ, that arc RQ, combines with QR to create RQR, or R, or PR, or excuse me, PR, right? Yeah. Very basic addition. Shouldn't overthink this. 2 minor arcs sitting side by side, add together to make a bigger arc. Or you know the measurement of the big arc and you know the measurement of one of the ones that makes it up, you subtract it to find the other one, right? Basic addition and subtraction properties. Okay? So the next page, they have you do that. Right? They give you that 1 is 75 and 1 is 65. What is it together? Well, we're going to add them together. And 75 and 65, 130 and 140. Okay, got it. Right? And then I'd know the other side. 360 minus 140 is 220. So I know it all the way to the other side. You can use the basic information and basic addition and subtraction to figure out missing arcs and central angles. Not very difficult math. All right? So turn a couple more pages. We'll finish up this section. We're on page 464B. 464B with a drawing in the middle. This is super important to put to memory. It shows 2 concentric circles, one inside the other. And it says, well, hey, ASD, if that's 60, then that means my degree measure of BC is 60 and my degree measure of AD is 60, and that's correct. The degree measures of your arcs are the same as the degree measures of your central angles, but the length measurements of them are different. So don't ever assume that because your degree measurements are the same, your lengths are the same. They're very different. Degree measurements and lengths are not the same thing. So these circles are similar, but they are not congruent, all right? Even though they have the same central angle, okay? So be very careful and remember that, all right? Then on the next page, 464C, it shows a theorem about congruent circles. In order to have congruent circles, 2 minor arcs are congruent if and only if their corresponding central angles are congruent. So this just shows that we have a circle on, basically the top of a circle, it's just one circle. It's using the vertical angle theorem. DQY is the same as WQX. They're both 30 degrees, therefore both measures of the arcs are 30 degrees. So they're congruent. The 2 minor arcs are congruent if and only if their corresponding central angles are congruent. Corresponding central angles are congruent. All right? So it shows that. So you would use that information to help produce other information. All right? Okay? So tomorrow we're going to review this and practice 11-2, our check for understanding, and then we'll take a quiz, or I'll probably assign a quiz for homework, all right? So that's the end. The bell's going to ring. That's 11-1, 11-2, a lot of information. I'm going to stop the recording and send the recording to everybody. I'd highly recommend you listen to it again, all right? And then we'll review tomorrow and do lots of practice with it, okay? the recording.